In 1997, humanity achieved a massive milestone by putting the Sojourner rover on the Martian surface. It weighed 11.5 kilograms and moved at roughly 1 centimeter per second. Decades of advancement have pushed our capabilities forward, but we are currently still only landing 1-ton vehicles. Escaping Earth's gravity well with just that 1 ton requires an immense launch vehicle and millions of pounds of thrust. Sustaining a human crew requires landing pressurized habitats, life support systems, and ascent vehicles. That pushes the required surface mass to anywhere from 40 to over 100 tons. Scaling a landing architecture from 1 ton to 40 tons requires a departure from incremental engineering into a field of entirely different physics. Sending people means leaving behind the expendable hardware model that defined the last 60 years of spaceflight. Human survival requires massive, closed-loop infrastructure designed to operate indefinitely. To bridge the gap between robotic probes and human settlement, engineers must sequentially solve 3 compounding physical constraints: orbital mechanics, heavy payload aerodynamics, and biological survival in a highly toxic environment. This maps a Hohmann transfer orbit. Spacecraft coast along a curved path, intersecting where the planet will be roughly 8.5 months later. If this alignment is missed, the planets drift out of phase. The next window opens in 26 months. Navigating this geometry requires a strict delta-v budget, which is the total change in velocity needed for the mission. A complete round trip from Earth to Mars and back requires roughly 30 kilometers per second of velocity change across multiple engine burns. Delivering that velocity using standard chemical rockets runs directly into the Tsiolkovsky rocket equation. Propellant mass grows exponentially with the velocity you want to achieve. Heavy payloads demand exponentially heavier fuel. One solution to bypass this mass penalty is orbital propellant transfer. Instead of launching all the fuel from Earth's surface at once, a spacecraft enters low Earth orbit, and separate tanker flights refuel it before the final trans-Mars injection burn. The alternative solution is nuclear thermal propulsion. Heating liquid hydrogen with a nuclear reactor achieves roughly double the fuel efficiency of chemical rockets. This could theoretically cut transit times to 4 months. Regardless of transit speed, the vast physical distance of the journey dictates a severe communication delay. Radio signals take between 12 and 22 minutes to travel one way. In a crisis, Earth cannot respond in time, making absolute crew autonomy an unavoidable mathematical consequence of the physics. When the crew arrives, they face the aerodynamic paradox of the Martian atmosphere. It generates 1,300 degrees Celsius of plasma heating upon entry, but at 0.6% of Earth's sea level density, it provides virtually no aerodynamic braking. To safely land a 1-ton rover, current architectures rely on a sky crane system, using massive 21.5-meter parachutes followed by a rocket-powered descent stage that hovers and lowers the payload on cables. This aerodynamic deceleration method faces a hard physical ceiling. Scaling it to a 40-ton human habitat causes the required parachute size and hovering fuel mass to compound until the vehicle structurally fails. The required engineering leap is supersonic retropulsion. This involves igniting high-thrust engines directly into a supersonic airflow to force deceleration, creating intensely complex fluid dynamics and shockwave interactions at the heat shield. While the Curiosity rover landed within a 20-kilometer ellipse, a human crew requires precision landing immediately adjacent to pre-deployed life support systems. Achieving this precision requires terrain-relative navigation. A 40-ton vehicle plunging through the atmosphere must autonomously scan the surface, compare visual data against preloaded maps, and execute course corrections in milliseconds. Landing humans on Mars requires entirely reinventing entry aerodynamics. The thin atmosphere demands thrust-based deceleration at a mass scale never tested on another world. The Martian surface itself presents a severe environmental threat profile. Decades of robotic telemetry revealed dramatic thermal cycling, with temperatures swinging 145 degrees Celsius between day and night, in an environment with zero breathable oxygen. Then there is the dust. Martian dust particles average 1.5 micrometers in diameter. They carry an electrostatic charge that makes them cling to mechanical joints, and they contain high concentrations of perchlorates, chemical compounds highly toxic to human thyroid function. Surviving these conditions requires in situ resource utilization, or ISRU. It is a physical impossibility to launch all the oxygen and return propellant for a human crew from Earth. The oxygen must be manufactured on site. Using a process called solid oxide electrolysis, already successfully demonstrated by the MOXIE experiment, atmospheric carbon dioxide is split at extreme temperatures to yield pure, breathable oxygen. To synthesize rocket propellant, engineers rely on the Sabatier reaction. By combining Martian atmospheric carbon dioxide with hydrogen extracted from subsurface water ice, a local chemical plant can produce liquid methane fuel for the return journey. Inside the habitat, human survival depends on a fully closed environmental control and life support system, or ECLSS. 100% of human metabolic waste, including urine and exhaled humidity, must be captured and recycled back into drinking water and hydroponic fertilizer. A Martian habitat operates strictly as a closed-loop chemical processing plant. Any architecture reliant on long-term Earth resupply is mathematically unviable. Outside the habitat, the absence of a global Martian magnetosphere exposes the surface to a constant influx of high-energy galactic cosmic rays. NASA's current career radiation limit for an astronaut is 600 millisieverts. A single round-trip mission to Mars is projected to expose a crew member to an estimated 1,000 millisieverts. The physiological unknowns extend to the gravity. Mars has exactly 38% of Earth's gravity. Long-term exposure to this partial gravity presents severe risks, specifically spaceflight-associated neuroocular syndrome and critical bone mineral density loss. The behavioral risks of a 900-day mission compound these physical threats. Analog environments reveal how absolute confinement degrades the human psychological architecture. Researchers studying crews at deep winter polar stations document the third quarter phenomenon. Roughly 3/4 of the way through a known period of isolation, cognitive performance drops, motivation declines, and interpersonal dynamics reliably collapse. Because remote telemedicine is impossible due to the communication delay, the crew must be prepared for extreme medical autonomy. They must possess cross-trained capabilities to perform major surgeries on one another without Earth's real-time input. The mission's most critical vulnerability remains the biological and psychological fragility of the human payload. This flowchart maps the interdependencies of a Mars outpost, the ISRU plant, surface nuclear power grid, life support, and ascent vehicle must all operate simultaneously. A failure in any single node, like power generation, triggers a cascading catastrophic failure, shutting down fuel and life support. This false color orbital map of an ancient river delta illustrates how we mitigate that risk. The last 60 years of expendable robotic probes mapped the specific geological parameters of Mars, converting unknown planetary threats into exact engineering requirements for ISRU-viable landing sites. The timeline for human arrival depends strictly on the empirical validation of these interlinked, mass-constrained technologies. Establishing a permanent human presence on Mars requires mastery over the laws of orbital physics, planetary atmospheres, and human biology at a civilization scale.